Okay, well the red light has come on, so I think that means I need to make a start. Apologies in advance that this lecture is going to be a little bit drier than yesterday. I was still hoping to do a nice demo where I could project my phone up onto the screen, but I still can't get Wi-Fi in here. I'm not sure why. I'll arrange to do a demo on my laptop on next Monday. I thought I would start just with showing you around the course. So I'm sure you know your way around my uni better than I do, but just so that you know, this is the course pages. If you go to the course page, you'll come to this, and if you want the lecture and tutorial schedule, you'll find it on here. Here are links to the 3 lecturers in the course and to Fabod, who's the tutor. Just a word about the textbook. Russell of Norway is a classic text. It's had numerous editions now. Some of the material is common to older versions. Newer versions have quite a bit of new material, as you might expect for a fast-moving field. We're going to follow much of what they do fairly closely, but there are going to be some differences as well. If you see something, for instance, up here, it says C1, that's indicating that we're covering material from Chapter 1 in Russell and Norway, for instance. Chapter 14 with a star, for instance, means it's related to, but not directly from, Chapter 14. And there may even be some material that's not directly covered in the book. It is available, I believe, I haven't checked recently, but it is available, I believe, as a sort of free download from the author's website. Likewise, I'm going to try and put lectures up. What you'll see in here, if you wanted to jump ahead and start downloading things, is lecture notes from last year. Be warned that they may change. The syllabus isn't going to change a great deal, but some of these may change a little bit in the content. This one is the latest version. The one that you see up here for Intelligent Agents is last year's version. I have this year's version on my laptop and I'll upload it. Virtually the same material, slightly different presentation, not very much difference in presentation. But if you wanted to download some of these, be my guest, but beware that I'm uploading the lectures as I sort of tweak them and rewrite them. That's all I wanted to say about this. Let's dive back into this today's lecture, which is going to be about intelligent agents. I'm going to have to, for some reason my laptop is showing really small on the screen, I'm going to have to read from up here. Okay, so we're going to talk about agents and their environments, the concept of a rational agent. I already introduced that idea on Monday. Talk about how we specify an agent in terms of performance, environment, its actuators and its sensors, and talk about environment types and types of agents. So first of all, what is an agent? It's a sort of nebulous concept. We're going to adopt this fairly broad definition that it's anything that can perceive its environment through sensors and acts upon that environment through actuators or effectors, things that can affect the environment. And we're going to adopt a fairly broad definition, so this is going to apply to virtual environments, software environments, as well as physical environments. So here's the another depiction of that picture that I showed you on Monday. So agents interact with environments through their sensors by sensing stuff about the environment and processing that sensor information together with prior knowledge to develop actions that they effect on the environment through, in our case, hands, legs, and so forth. But in the case of other agents, in the case of a software agent, the inputs may well be keystrokes, file contents, network packets, and so forth, and it may act on the environment by displaying stuff on the screen, writing files, changing internal states, sending network packets, and so forth. so a game agent, for instance, would be like this. It's written as an entity, an object in object-oriented speak, and it would have a set of well-defined inputs and a set of outputs that it affects by changing the environment, affecting other objects, and so forth. If it's a robotic agent, then the sensors are typically going to be things like cameras, or maybe a LiDAR sensor, or sonar. Perhaps it will be encoders for joint angles, things like that. And the actuators are going to be things like the motors that move arms or that cause a gripper to close, and so forth. Obviously, for a human agent, so working my way up the slide, eyes, ears, other things, proprioceptive things like your inner ear that's giving you inertial measurements about your movement and so forth. And then your actuators are things like your legs and your hands and your voice for affecting the environment. So, a bunch of boring, dull, terminological stuff. So we're going to define the performance measure of the agent. This is the criterion that determines how successful an agent is. We'll be a little bit more specific about that later. The behaviour of the agent is the action that the agent performs after any given sequence of percepts. After that may be a single percept, or it may be a sequence of things that it perceives in the environment. A percept is a thing that the agent's the agent perceives at a given instant. So that will be through its sensors. The stuff that I'm perceiving is through my eyes, through my ears, touch, and so forth, and I act corresponding to what I'm perceiving. The percept sequence is the history of all that an agent has perceived to date. It may act on that entire history, or it may act solely on the thing that it's perceiving at the current moment. We'll talk a little bit about that later on in the lecture. And the agent function, so this is quite important. The agent function is a mapping from the percept sequence, so the things that the agent is finding out about the environment, to an action. So its implementation is called the agent program. Okay, so the agent function, as I said, maps from the percept histories into action. So think about this mathematically. I promise it's not going to get more mathematical than this. It's just a mapping that we'll call F from a percept history to a particular action or actions at a given instant. And the agent program runs on a physical architecture. So together, the architecture and the program comprise the agent. So obviously we need the architecture to be consistent with the program and vice versa. We don't want a program to recommend actions that are physically impossible. So if we're going to recommend actions like walk, then the architecture better have legs. Your agent program shouldn't recommend an ordinary car to fly. Perhaps if I could ground this and go a little bit off script, I showed you a video of a robot picking stuff in the last lecture, and that was inspired by some work that we did in conjunction with colleagues at Queensland University of Technology, entering into the Amazon Robotics Challenge. The Amazon Robotics Challenge is trying to pick things from bins. We entered the same competition last year as well, and we did so with a Baxter robot, and Baxter would stand in front of a set of shelves and have to reach in to a shelf and pick objects off. One of the things that was deeply frustrating to the team trying to program this was that in fact they couldn't get a very good match between the architecture, which was Baxter stood in front of a set of shelves, and the actions that they were asking it to perform. And the reason is that the reach of Baxter is actually not very far. And so you put this robot that you think, oh, it's a bit humanoid-like, in front of a shelf, and it would move to this point here, right in front of the shelf, and you say, okay, all you need to do now is move forward by 10 centimetres to pick up the object. And it would quite often do one of two things. It would either just stand there and go, and it couldn't move because it was physically outside of its workspace. Or it would do something really weird like and come back almost to exactly the same place. But very, very strange. We were asking that agent to do something that it was not physically possible to do. But in fact, because the guys who were programming the system didn't fully understand the relationship between the kinematics and the dynamics of the robot and the workspace it was working in and so forth. So these may sound like flippant examples, but actually it's a real problem, matching your architecture to what you want it to achieve. So we're going to start with a really, really simple. This is going to seem a bit of a brain-dead simple example. However, it's going to get across some of these concepts. So we'll talk about a very simple, discrete, vacuum cleaner world in which we have an agent, and the agent's role is to clean up the environment. And let's suppose that the environment consists of just two locations, A and B, and that the agent has two percepts. It's able to perceive where it is. Is it in room A or is it in room B? And it can perceive whether the environment is dirty in each of those locations. So it's got these two percepts at any one time. So this particular one is A and dirty, it would perceive. The actions available to this very, very simple agent are going to be, it can move left, it can move right, it can suck, or it can do nothing. Okay? So those are four possible actions. And the agent function, in this particular case, is just going to be a fairly simple lookup table that maps whatever it perceives at a particular instant to what it's going to do. So this is just, in this case, not a very large table, but for some agents, this could be a huge table. And for other agents, it's intractable to enumerate all the possibilities, and we'll come to an example of that later. But for the purposes of this, we can map all possible percept sequences to an appropriate action. So if we're in room A and it's clean, then the appropriate action is to move to the right. It takes us to a new location. Our work here is done. So if we're in A and it's dirty, then we should suck, and hopefully that's going to result in a change to the environment so that it goes from being dirty to clean. If we're in B and clean, then we'll move to the left, and so on. Okay? So you can see that we can generate a table of actions that correspond to the current percept. So this is our agent function. We could even start to enumerate all possible histories. In fact, the possible histories here are going to be very, very repetitive. So it's going to be unnecessary to repeat them ad infinitum. But we may want to look at if A clean and then we observe A clean, then we might want to move right. Perhaps we've mistakenly at some point put in if A is clean, move left. And if we move left, actually what happens is that nothing happens because we stay in the same room. So here's our really simple program. And again, sorry, maybe this seems a little bit patronising to start with something so simple. You guys, I'm sure, are all expert programmers, but I'm just trying to emphasise the idea that what we're talking about with an agent, you guys can think about it as just being a function that lives on a particular hardware implementation, a particular architecture. So here's our program of a reflex vacuum agent, and I'll define what I mean by a reflex agent later. It takes in two inputs, the location and the status. So these are the percepts. The percepts are the function arguments. And it returns an action. So this is a really simple lookup table. It just says if the status is dirty, then the action is suck. If the location is A, then we're going to go right. If the location is B, then we're going to go left. So it's an incredibly simple function, and this will carry on working on our architecture. And hopefully, you can imagine that this could be arbitrarily complex, taking in percepts, and we'll talk about more complicated agents where perhaps we've got some internal memory in here as well, for instance. You can think of those as being static variables to the function. So what's the right way to fill out this table? What's the right way to map from percepts to actions? How do we go about designing our agent so it does something sensible? What makes an agent good, bad, or intelligent, or stupid, or what? So I talked about the idea of rationality and that we were going to use that definition throughout this course. So a rational agent, or an ideal rational agent, is one that for each possible percept sequence, a rational agent should select an action that is expected to maximise its performance measure given the evidence provided by the percept sequence and whatever built-in or prior knowledge the agent has. Okay? Let me just let that sink in a bit. It's going to select an action that should maximise its performance measure, given the information that's available to it. And the information that's available to it is any kind of built-in or prior knowledge it has, and what it is sensing at the current time, and what it has sensed over history. Of course, the devil is in the detail. What do we actually mean by the performance measure? So the rationality depends on, critically, on this performance measure that defines the criterion or the multiple criteria for success of the agent. Prior knowledge is prior knowledge about the environment, stuff that perhaps has been coded in by the designer, or perhaps information that has been bestowed upon the agent by some oracle. Obviously the actions are the things that the agent can do to the environment, and the percept sequence is the things that have been observed about the environment from the start of time to now. Note that rationality doesn't necessarily mean perfection. In an uncertain world, we can't possibly make the perfect decision every time. What rationality does is to maximise the expected performance. Perfection would be to maximising the actual performance, but we can't ever do that in an uncertain world. If we can't be certain exactly of the consequences of our action, then we can only maximise the expected performance, not the actual performance. And rationality doesn't necessarily mean omniscience. It just means that we will act in a way that, to the best of our knowledge, will maximise our performance. So our percept may not supply all the relevant information. If you go and look in Russell and Norwig, there's a slightly flippant example talking about seeing a friend on the other side of the Champs-Elysees in Paris, and wave to the friend, and the rational thing to do, if it's someone that you haven't seen for a long time, is to, and you look and you see that there's no streets on, no cars on the Champs-Elysees. This must be 3 a.m. or something. I don't think I've ever seen the Champs-Elysees without lots and lots of cars on it. But so you see this friend, and the rational thing is to walk across and say hello. What you can't anticipate is that a fridge has been dropped from a plane whose cargo doors have failed and is going to flatten you halfway across. It's still a rational thing for you to cross the street. You have acted completely rationally, even if you haven't achieved your goal of saying hello to your friend and you've ended up splattered across the Parisian capital. Okay, so different example. In a card game, you don't know the cards of what other people are doing. All you can do is maximise your expectation of your own performance. And one final definition. You'll hear a lot about autonomous systems, either in this course or as you go through this degree. So an agent is autonomous, for our purposes, to the extent that its behaviour is determined by its own experience. So something that has been hard-coded into an agent is not necessarily something that we would say is autonomous. The example given in Stuart Russell's textbook is of a watch that automatically resets itself as you go through time zones. And he says, well, that's doing something that is sort of autonomous, but for our definition of autonomy, that's not autonomous, because that's something that the designer plugged in right at the start. That's not something that the watch is doing based on its own experience. Sorry?
The alpha zero is the alpha go. The alpha zero is self-training, and the previous go map is just itself.
Yeah, yeah.
So it's own experience.
Yes. Well, exactly. So that is an autonomous system. Yeah, by that definition. Yeah.
Is the logic control between something that's autonomous and not autonomous arbitrary? Because
it's going to be a little bit like the definition of intelligence. Gets moved as things get as we achieve different competences. We might look back and say, well, actually, it's not really autonomous. Okay, so have I gone? Okay, so to define the problem, this weird acronym PEAS. So performance measure, environment, actuators and sensors. So we need to specify the setting for the design of our intelligent agent. And so consider the task, suppose you're working for Uber. You've done this course and you go off to work for Uber and your task is to design a taxi service. Now the likelihood is that they will have done that before you guys graduate, but there'll be something else like this. So you start out with a performance measure. How am I going to measure the performance of my autonomous driving taxi cab? So clearly consumers are going to want it to be safe and fast. It's going to need to be legal. Consumers are going to want it to be comfortable. And if we're coming from the perspective of Uber, then we want to maximise our profits as well. So those are the things that are going to be used to measure the performance of this autonomous taxi agent. The environment is clearly going to be roads, and it may well be in the first instance just urban roads. Perhaps we're just going to concentrate on an inner city, for instance, but we're going to have to worry about probably other traffic and pedestrians and so on. Maybe we don't. Maybe we can have some legislative framework where we are the only operators in a particular area. Our actuators, pretty clearly, for an autonomous driving car are going to be steering wheel, brake, accelerator, and various signals like indicator, horn, and so on. And the sensors are whatever sensor suite we believe that we're going to need. The likelihood is we're going to need some cameras so we can read road signs. Likelihood is we're going to need some GPS so that we know where we are. Maybe GPS isn't going to work all the time, so we need to use that in conjunction with cameras. Maybe a LiDAR sensor, so a laser rangefinder for mapping our environment. We probably need some engine sensors and so forth. So those are the sensors. So there's our PEAS, our P, performance, environment, actuators, and sensors. Now I'm going to spend some time talking about the types of environment that you might need to deal with when you're designing your agent. And we're going to classify them as in these 6 different cases. And different cases will have different combinations of each of these. So fully observable versus partially observable. If it's not observable at all, then there are no percepts. So perhaps it's not a particularly interesting environment. Deterministic versus stochastic, episodic versus non-episodic or sequential, static versus dynamic, discrete versus continuous, and single agent versus multi-agent. So first of all, fully observable, or in the words of the textbook, fully accessible is the alternative notation. Is everything that an agent requires to choose its action available to it via its sensors or in its internal memory? If so, then the environment is fully accessible. Okay? So it just needs everything that is necessary for it to choose its actions. If parts of the environment are not observable, then we say that the environment is inaccessible. The agent's got to make informed guesses about the world. And so I guess in the terminology of decision theory, we talk about perfect information versus imperfect information. So I'm going to do just a quick 2-minute pause here. You got, what's that, 6 things down the bottom. Grab a piece of paper, either on your own or with the person next to you. I want you to decide, doing a crossword, does that have a fully observable environment or any partially observable? Poker, backgammon, are these fully observable or partially observable? Taxi driver, part picking robot, and some random image analysis. You've got 2 minutes. Have a think about it. And I'm going to pick out random people from the audience to give me an answer. So do think about it. Okay, I think that's enough time because I've got a few more of these to do later on in the lecture. Crossword. Anyone like to volunteer? Fully observable or partially observable? Oh, there's got to be someone down here in the front. Fully, yeah. Okay, we've got fully for crossword. Poker. Partially? Why partially?
Because you don't know what else you have.
Exactly. You know your own hand, but you don't know what you're going to be dealt in the future, and you don't know what other people have in their hands. Backgammon. I reckon backgammon is fully, because you know exactly what's on the board, and you roll the dice, so you know exactly what your options are at any one time. Yeah?
You don't know what the roll's going to be. The dice roll the phone until you roll the dice.
So, once you roll the dice, I'd say it's fully observable. Yeah? But you're right, you don't know how the dice are going to roll. So if you're assessing what your position is before you roll the dice, then in a sense, it's not fully observable.
But in that same, like, depending on how much computation power you have, you look at many possible options and fully understand.
Well, yeah, but so your branching factor there is what is it? It's more than 12 because it's actually what's on the it's actually what's actually on the dice that makes a difference. So it's whatever your branching factor is 20, something like that. You might struggle, but there are very good backgammon playing programs that can achieve pretty much perfect play by maximising their expected return. Okay, taxi driver. Pretty obviously, it's not fully observable. Okay, it would be nice if it worked, because then we could be sure that our taxi driver is not going to crash. How about a park picking robot? Someone up the back. Okay, good point. So this one is going to be a big question mark because it's going to depend a lot on what our environment actually is. And if it's the same part and they don't overlap, then I guess the environment is fully observable. But if it's possible that there might be things out of our field of view and so forth, then potentially it's not fully observable. Image analysis, well, I put fully question mark there. I think it depends very much on what the task is. Okay, so deterministic versus stochastic. What I mean by deterministic versus stochastic is, does the change in the world state depend only on the current state and the agent's action? Okay, so that would be a deterministic world, meaning the world is going to evolve in a completely predictable way based on the way the world currently is and what I do to the world. So let's think about, I'm going to give you the answer for the part picking robot. Assuming all other things are equal, then potentially we could say that the world for the part picking robot is deterministic. Fixed number of parts, and they're all static on a bench, and we're going to go and pick up one and move it to another location. And if we assume that it's not going to knock other parts in some unpredictable way, then we can say that it's deterministic. Okay? But if we can't predict because there are other factors in the environment, then we would say that it's stochastic. So non-deterministic environments have aspects beyond the control of the agent. And typically, we're going to need to have something like a utility function to enable us to guess at changes in the world and guess at what might be our best action under uncertainty. Okay, 1 minute to have a think about what each of these are, deterministic or stochastic. that's less than a minute, but in the interests of making sure I get through all the slides in the lecture, let's cut that short. I won't do a poll of the audience, but here we go. How did you go? I reckon crossword is deterministic. Poker pretty clearly is stochastic. Backgammon is stochastic because we can't control how the dice are going to land. Clearly we can't control the rest of the world, other drivers. We can't control dogs running out in front of us and so forth. Part picking robot, I think this one's up for debate. It could be stochastic, it could be deterministic, depending on how good our robot is and so forth. For a real implementation, it's probably going to be stochastic. Image analysis could well be deterministic. We put the same image into our program, the likelihood is we'll get the same output every time. So, episodic versus sequential. What I mean by episodic is the choice of the current action dependent on previous actions? If not, then the environment is episodic. Okay? So can we make a choice of our action completely independently of what's happened before? So in a non-episodic environment, then typically what we have to do is some kind of planning. Okay? So our current choice is going to affect what we do later on. So there's a need for us to plan in a sequential or non-episodic environment. Whereas in an episodic environment, there's no need to plan. We can just say, at this particular point in time, I have full knowledge, I can make this action and not worry about how that's going to affect things later on. Okay, I won't go through these, but in your own time, you can have a look at those answers that I've given you there. And likewise, static versus dynamic. So a static environment is one which doesn't change over time. Or in particular, for the purposes of an agent, then a static environment is one where it doesn't change while the agent is deciding what to do. Okay, so that's a slightly broader definition. We can allow the environment to change, but we want to be able to sense the environment, whereas a dynamic environment would be one where it may be evolving in ways that we can't necessarily sense. We might have to predict. So a dynamic environment changes, so the agent needs to consult the world when choosing actions, or it needs to anticipate the change during its deliberation, or perhaps make its decisions really fast. Yeah.
So is it safe to say that any stochastic environment is also static?
You say a stochastic environment is also static. No. If I've understood your comment correctly, I think it would be fair to say that most real-world dynamic environments are stochastic, and the reason is that we are very unlikely to have a good dynamic model that can perfectly predict how the world will evolve. But I think that you were saying the converse of that. Is that right?
Well, because when we're saying stochastic is when the environment doesn't change unless the agent acts on it, in which case if the agents are not acting.
Stochastic means it's uncertain, as opposed to static.
Sorry, I think it's deterministic.
Okay, yeah. Come back to me after the lecture, right? Okay, yeah.
That your actions will have an influence on the environment, but the environment will change
Okay, yeah. So this, I believe, I'm sorry. I think I've left some words off the end of the sentence here. But the intention here is to say that the environment itself doesn't change except as a result of the influence of the agent. I'll come back to that after the lecture as well. Yeah? Okay, so you can have a think about those offline as well. Finally, discrete versus continuous. And in some problems, it's absolutely clear that the environment is discrete. In some problems, it's absolutely clear that the environment is continuous. And then in some problems, it makes sense for us to take what is a continuous environment and discretize it in some way to make the problem tractable. But for some of these things, okay, clearly a crossword, poker and backgammon are discrete problems. There are countable events that can happen. There are a very big but a finite number of hands that you can possibly hold, finite number of cards that you can possibly be dealt. So they can be represented as discrete states, discrete entities. Whereas you can't describe the world that the taxi driver experiences as a set of discrete entities. It's a continuous world. The speed is not one of 10 things. The taxi driver's speed is a continuous range of values and so on. Okay, so again, you can have a think about what those answers will be. And then finally, single agent versus multi-agent. Quite clearly, this is referring to there being one agent acting in a particular environment versus potentially multiple agents in a particular environment. So clearly crossword, you do that on your own. Poker, multiple agent, okay, you're playing multiple people. Backgammon, two players, two-player game, so multi-agent. Taxi driver, clearly there are many agents in this particular environment. Cart-picking robot is probably a single-agent environment, but maybe it's cooperating with a person, or maybe it's cooperating with another robot. So it might be either image analysis, almost certainly this would be a single-agent environment. Okay, and then just a sort of a pointer to some stuff that I'm going to talk about later. Well, in fact, we'll get to later in the course. If the environment is fully observable and the environment is deterministic, then the likelihood is that some kind of search criterion or some kind of search algorithm is going to be helpful in maximising the performance of our agent. So we're going to spend some time looking at search techniques and how we can turn what could be a very, very big search into a tractable search over the next few lectures. If these things are not true, then we potentially have to deal with uncertainty, and that's, we're going to address that in the last few lectures of the course when Ling Chao takes over. And in the middle, there's going to be a chunk about learning as well, just because learning has become so very important in artificial intelligence. Okay, so the last few minutes of the lecture, I want to talk about how we go from a problem that's specified by these performance environment, or whatever the A and the S are. Rational agents are our solutions to the problem. Okay, so the job of AI, the job of you guys as AI programmers, is to design the agent program that implements the agent function, the mapping from percepts to actions. So a bunch of different agent types. I've already alluded to these over the course of the lecture. So a simple reflex agent is one that selects its actions on the basis of the current percept. It ignores the rest of the percept history. It's a reflex agent because it reacts immediately to whatever it's seeing, whatever it's sensing at the current moment. So our robot vacuum cleaner, very simple vacuum world, looks at what room it's in, whether it's clean or dirty, and it does a thing. Without reflecting on that at all, it just does it as a simple reflex. A model-based reflex agent has an additional component. It has a model of the world that helps it choose its actions. So they're maintaining not just what am I currently seeing, but some internal state, perhaps some memory of the world. These two might be useful for some things, but they'll do stuff. But will they do useful stuff? So we refine that into a goal-based agent, where a goal-based agent is choosing the actions to achieve a particular goal. And in particular, we're going to talk a lot about search over the next few lectures. You'll find that in chapters 3 to 5 of Russell. We will talk a little bit less about planning, but if you're interested, go and have a look at chapters 10 and 11 of Russell. So these are subfields of AI dedicated to finding the action sequences that achieve the agent's goals. And then finally, we might have what we're going to call a utility-based agent, one that has a goal, but perhaps there may well be actions that all lead to the same goal, and now we have to have some kind of preference for an action sequence that leads us to a particular goal. So a utility-based action is one that's perhaps going to, maybe there are conflicting goals and only a few of them can be achieved, or perhaps the goals have some uncertainty of being achieved, and what we're going to try and do is weigh up the alternatives and decide which is most achievable, or which is achievable in the least amount of time or with the least amount of cost, and so forth. And just coming back to the importance of learning, all of these can be turned into learning agents. The idea of a learning agent is one that can observe and do better next time by having seen more and more data. Okay, so a simple reflex agent here is an implementation of a simple reflex agent. So we have the environment, the sensors give to the agent some knowledge about the environment, tells it what the world is like now, and it has this set of condition action rules. What am I seeing? What should I do? And that tells it what action it should do now, and it has its actuators. So here's a return to that very simple reflex vacuum agent. So, very simple, very limited intelligence. The action does not depend on the percept history, only on the current percept. So there's no memory requirements. Unfortunately, this can lead to some pretty stupid behaviours, typically infinite loops. So I mentioned if we had made the mistake of asking the robot vacuum cleaner to move left when it's in room A, then it would just keep doing that and get stuck in that loop. One way around that might be to do some kind of randomisation of the action. Perhaps there might be two possible actions, move left, move right, and we just randomise. That would help us get out of an infinite loop. But we witness this in nature as well. So moth flying around the light, and it has this instinct to fly towards the light, and it just keeps going around and around. It has no memory of the fact that it's done this 12,000 times already tonight. It just has this instinct that getting close to the light is a good thing to do. Okay, so if we think about a chess-playing agent, then openings and endings are things in a chess game that you can typically enumerate. And so you might have a lookup table for the opening few moves of a chess game. You might have a lookup table for how you close out a particular game from a particular state, because there are certain configurations that occur quite frequently. But it's probably not a good idea to have a lookup table in general for a chess game, because you would have 35 to the power 100 entries required for the entire game. So a lookup table perhaps not, well, certainly not tractable, definitely not a good idea. So a model-based reflex agent adds this component over here. It's got an internal representation of the state of the environment, or of its state, and it also knows how the world is evolving. So for instance, it knows that a car that's approaching from behind is going to get larger in the rear view mirror and so forth. It knows how it will affect the world itself. So if it's a self-driving car, it knows that if it turns its steering wheel actuator to the right, it's going to tend to move to the right, and so forth. Well, turn clockwise, sorry. It's going to tend to turn to the right. And these model-based agents update their state. So here's a very simple implementation of that. Remember, it's still just a function. It takes a percept in as its input and it returns an action. But it has these static variables in here. So these are variables that are local to that object, local to that agent, but which maintain their value over time. So these are the internal memory of the agent. So the first thing it does is it updates its current state on the basis of the percept. So it updates its internal representation of itself and the environment. Then it matches the rule to the current state and chooses an action based on its set of action and rules. So it knows what its actions do, and so it can predict what rule it should pick, and then it does a final state update so it knows how the environment will evolve according to its action as well. So a goal-based agent recognises that knowing the state and the environment is not enough. Okay? You need to have, just because you're a taxi driver agent, you need to get somewhere, a destination to get to. So it uses knowledge about a goal to guide what action it should take at any particular moment. So a goal-based agent adds in this thing in here, this question here. What will it be like if I do action A, and does that get me closer to my goal in the long run? A reflex agent is always going to brake when it sees some brake lights, whereas a goal-based agent is going to reason there's a brake light in front of me, the car in front is stopping, I should probably stop, I should probably use the brake. But there may be other actions, because it may be that the car braking in front is braking because it's about to turn left. And the goal-based agent knows that it wants to carry straight on, so perhaps it doesn't have to take this reflex action immediately. It can reason about what the consequences of its action might be. Utility-based agents recognise that goals are not always enough, particularly when we've got an uncertain environment. We might have many action sequences to get our taxi to a particular destination, and perhaps we want to consider other things. How fast we get there, how much fuel we use, how safe it is to get there, and so on. So a utility function maps a state onto a real number which describes the associated degree of success or goodness, or if you want to think about it as happiness of the agent. And there are various ways we can devise utility functions. In economics, it almost always comes down to money. How do we maximise the monetary payoff of a particular set of actions? In biology, in natural selection, it probably comes down to either number of offspring, or perhaps more appropriately, the fitness of the offspring. You might want to reflect on what are your utility functions? What drives you? Just out of interest, how many is it money? You've got one honest person. Cool. Okay, so utility-based agents. So we have this utility. How happy will I be in such a state? What action should I do now? Looks like it's about to stop recording. So, more about learning. There's my summary. You guys can read the summary later. I'll finish there.
So I said stochastic, I meant deterministic.
Oh, right,
I got
okay.
it messed up in my head.
Okay.
Probably because stochastic sounds like static.
So what was the question?
So, getting up the slide. So deterministic is the world state only changes when the agent acts. And then static is that the world doesn't change when the agent doesn't act. So then, in my head, what's the difference between the two?
So deterministic is the world is completely predictable.
Yeah. Okay. So if it's like the taxi driver, then you would say that you can predict how fast it's going, but it's not static because it's still moving. So it's like you know what the acceleration is, so you can determine where it will be, but it's still moving. Is that what you mean?
So I'm still not sure of the distinction that you're drawing. The distinction I'm drawing is that something is stochastic if you can't make a prediction, a perfect prediction of it, which is different from it being static versus dynamic, because you could have a dynamic environment that is perfectly predictable.
Okay.
So for example, a ballistic missile is dynamic, but it's predictable.
Yeah.
That's the nature of it being ballistic. You set it going, and it will carry on.
So I guess what I was trying to say